Let's continue our expert talks. Our next speaker suggests the transition of musical style as one of the most popular tasks for automation of music generation with the use of AI. Our next speaker will be talking about mathematical models that allow to analyze characteristics of musical compositions and transfer musical style from one music onto the other with AI. Please, the representative of Huawei, the title sponsor of our conference, the expert for voice biometrics of Huawei Research Center in Moscow, Mr. Ivan Shanin.
Ivan, good afternoon. We're looking forward to your presentation today. Let's see what's interesting about the technology. How is it innovative? Over to you. Good afternoon. Yes, my name is Ivan Shanin. I work for Huawei at Multimedia Algorithms Department, and today we're going to talk about neural network music generation, exactly transfer of music style with the help of AI. To begin with, let us have a look at style transfer that is well known to everybody, to all enthusiasts and professionals. Style transfer in images. These style transfer is done quite easily because there was found a very great way to do that, and style was done a great way here. It turns out that if you believe that texture is the style, then in this matrix, gram is very suitable to describe the style. And those images where matrix gram in different layers are close to each other, then those images are most probably going to have a similar texture. But it's more difficult with music. It's much more complicated here. To begin with, let's consider what music actually is, and let's define the terms. Traditionally, there is a composer who writes the music. He writes the music usually in notes, music notes. Then the music has a performer who performs these notes and turns it into some actions. For instance, presses the keys on a musical instrument, for instance, a piano, like in this case. Then the instrument kicks in, it turns this action into fluctuations of air. They are perceived as the sound, and the listener listens to this sound and interprets this music. So it's a multi-layer process. What is a musical style? It's a difficult question, and there are a few answers here. This slide illustrates a few demonstrations. Let me demonstrate what I mean. Let's begin with the first one. You have listened to a music tune in the style of classical piano music. However, this style is cannot be described by classical music only. Here is another option of the same composition. Excuse me, Ivan, excuse me for interrupting. We couldn't hear the first tune and we couldn't hear the second one. Okay, let me play them again. Thanks. Yeah, maybe some technical error. Now let's listen the second version. So you have heard that notes are the same, but they're played with different instruments. In the first case, it was piano only. In the second case, it was orchestra music. The context is the same, but the style is different. Let's listen to the third option now, to the third example, in order to understand how diverse this task might be. So you can hear that the same song performed by the same musicians, but in the first case it was done in home environment, but in the second case it was played by a full-scale band in a studio in a professional way. So music context is different because different musical instruments are playing different parts here, but it's perceived as the same song. Thus, style can be defined as changing the arrangement, changing musical style, or changing the set of musical instruments and changing different voices of instruments. Why do we do it? So why do we do it? What motivates us? First of all, it's interesting to create different collaborations between artificial intelligence and musicians, professional musicians and amateur musicians. Professional musician will be interested in creating new sounds or new instrumental sounds or bring new aesthetics to his music. For instance, in visual art, it is already well known that AI brings such a style as glitch. It is called glitch. In music, I guess it's the same. But an amateur musician might use these instruments or these tools in order to improve the quality of his sound and in order to improve his tunes, or in case if he doesn't have enough skills in using different musical instruments, he might improve the rhythm or improve the sound of these musical instruments. This is the way it can be done. Let's begin by explaining how we convey musical data into our computer, how AI perceives them. The well-known representation, the most raw representation is waveforms. And with waveforms, there are a few difficulties. First of all, they cannot be interpreted visually. It's hard to understand just looking by the picture what exactly was said or played. And they're quite heavy, they're quite thick, because 1 second of this data has 44,000 of values, and without any computation, it's impossible to analyze this data. The standard way to overcome it is switch to a spectrogram with a Fourier transition. This way, data represented more like an image, and at every point in time, you have a vector of values that describes frequencies that are performed in every box. It is easier to tell something by this data. You can see that there is some rhythm, that there are some cells or boxes that could be played by a musician at every point in time. Both representations are representations of musical data, but there is also analogs of music notes that are called MIDI. MIDI, and this representation is visually similar to a spectrogram that was in the previous slide, and the point is that MIDI is a symbolic representation. It represents a list of commands, which note should be played with what timbre, so on and so forth. To some extent, this is a new way of notes, and modern electronic music is using similar formats, similar to MIDI, and they are not recording their music in notes anymore. What else is great about MIDI? Oftentimes, when we are training neural networks or when we are generating music in different methods, we want to switch from music format to symbol format. And thus, we're doing music transcription. But that's not what we're going to discuss today. We're going to discuss something different. What's the reverse task? The opposite task to music transcription is music synthesis or sound synthesis. According to some understanding, media recordings or latent representations, we're interested in algorithm that creates music or audio signal which gives wave form that will sound like a sound file. And the outcome. There are different methods for that. The most popular one is the network that's called WaveNet. The main idea behind it is the deployment network. It deploys and expands attention span every time exponentially. Let's get down to style transfer, exactly. And let me demonstrate here, or let me show a few neural network architectures that solve different aspects of this task. We have already discussed that there are a lot of aspects there. And let's begin with the architecture that became available recently. It transfers music timbre, and it's a trained synthesizer. This architecture, just like many other architectures, is an automatic coder, autocoder. So initial music data are encoded into some latent representation. In this case, it's very simple. It's just frequency of the tone plus some latent variables and some loudness, exactly loudness of the signal at every point in time. And based on this data, the network is recovering the signal, but uses additive synthesis. It uses harmonics of the signal. When training the network, it filters the noise that is present at the recording, the additive noise, and also there's a filter applied which does reverberation, which is in line with the ambient environment at every point in time. During the training process, this network learns to generate the signal, which is as similar as possible to the initial signal. And it turns out that the outcome decoder can be used as a synthesizer, and it can be trained on data sets that contain sounds of specific musical instruments such as violin or saxophone or voice. Another aspect of style transfer is done with the help of this architecture. It is called Universal Music Translation Network, and here we can find some familiar elements. This network is encoder-decoder network as well, but as an encoder, they use WaveNet architectures that work with raw signal. This network helps transfer texture of one sound to another sound. Texture, I mean in brackets. And it makes transfer among such sounds as whistling and guitar or an orchestra, and it has quite the result is quite impressive. Another network that recently became popular is Jukebox. Authors of this network had a task to resolve the following problem. When you generate music, you need to take into account long-term dependence among data. What was played a few seconds ago or a few dozens of seconds ago, what is played half a minute ago even, might impact the sound that is being made right now, because structure of music is quite complicated. So they use neural network that is called VQVEE, variative autocoder of spectral coding. And authors, it took authors a lot of computing power to achieve great results. Thus, another feature of this architecture is that the representation within the coder-decoder, they are discrete, and models trained on this network allow to generate music that is in line with the style of this performer, or that is in line with the words that we would like to have in this specific song. This is why this architecture is a more high-level architecture to change musical style. It helps to regenerate completely music file, and it generates a completely new type of music, which, in terms of style, it will remind completely what was in the latent part of this architecture. Up until now, we have been speaking about changing the music style in the domain of raw audio files. However, in symbol domain, there are also some interesting architectures that allow to change music style this way or another. For instance, there's architecture that transfers music style in order to do some training of the systems, and it uses parallel data that were generated by algorithms. There are also architectures that are based on encoder-decoder algorithm. As an encoder and decoder, we use transformer in this case. And it's not comprehensive yet. There is another way here, another option. There is an option when one style is transferred to, one music style is transferred to another music style, but sometimes authors would like to transfer style among different domains, so cross-modal. Just like on this style, there is a music transfer, there's a style transfer among music to visual, music to image, or image to music. We take a music file, sometimes we determine the style of this music file. I'm sorry, we take an image, we define an impeder that defines the style of this music composition, and you can see that as a result, we see an adjusted image which is more in line with the music. This task might be useful when you generate a soundtrack automatically for some user videos or for some more professional movies. So there's a cross-modal style transfer among music and images. On top of that, there might be a task to transfer style, to transfer mood from one song to another. Not just style, but also mood from one song to another. You can try to combine different music compositions so that their mood is close to each other, and there are also interesting solutions for that based on AI. And one more aspect of this review is algorithms of identity, vocalist's identity transfer. So you can generate a composition and make it sound like it's not this person is singing this composition, but a well-known singer is singing this. There's an abundance of interesting methods to imitate singing of well-known singers. In conclusion of my presentation, I wanted to give you a list of unmet problems yet and challenges that this area still has. First of all, it's difficult to define what is a musical style. And there are no data sets that would define it. They just don't exist, and they cannot exist. It's impossible. Moreover, AI cannot be used to judge a piece of art, because AI might judge whether one tune is similar to another tune, but a new piece of art can be perfect to a human ear, but AI will not be able to understand it. At least this is the way it is right now. And the final problem is that musical traditions that the majority of musical tunes have been generated based on these musical traditions is Western musical tradition, and sets of data that correspond to different folk music, for instance, Indian folk music or Chinese music or Russian music. These data are hardly present. And there are a lot of people listening to this music, and the impact of this music on the world is quite massive as well. Thank you very much. My presentation is over here. Thank you for your attention. Thank you very much, Ivan. It was an interesting presentation, a great lecture, so to speak. Thank you for your participation. And what's going to happen next? Right now, we're going to have a small break. And after this break, we're going to witness and we're going to take part in a very heated discussion, a small break.